July 1st, 2025. A faint, barely noticeable pixel drifts across the sky. It's subtle but not invisible, and it's soon detected by the ATLA's telescopes in Hawaii and South Africa. The object's movement is odd, its velocity is unusually high, and its path through the solar system isn't looping or elliptical. It's sharply hyperbolic, an unmistakable sign that this is no local object. Astronomers quickly run orbital calculations, and a striking conclusion emerges. This visitor is interstellar. Only the third ever detected after Comet 2I Borisov in 2019 and Oumuamua in 2017. The new object is named Laius. Early imaging reveals something more. It's active. Surrounding its core is a visible coma, the cloud of gas and dust that typically forms around a comet. That alone distinguishes it from Oumuamua, which showed no signs of outgassing whatsoever. Instead, Atlas seems more behaviorally aligned with Borisov, which behaved like a conventional comet. But this similarity raises a deeper question. If both Borisov and Atlas followed familiar cometary patterns, why did Oumuamua behave so differently? How did it pass through our solar system without emitting gas or dust, or even being spotted until it was already on its way out? With the discovery of 3IATLAS, Oumuamua seems even more unusual. Rewind to October 19, 2017, Pan-STARRS 1 is surveying the night sky when, at 1:22 a.m. Hawaiian Standard Time, a streak flashes across the image frame. It moves far too quickly to be a nearby asteroid or typical space debris. Just hours later, astronomer Robert Warwick at the University of Hawaii examines the data and notices this rapid-moving object. It's clocked at 26 kilometers per second and has an orbital eccentricity of 1.20 clear signs. It's on a hyperbolic trajectory, destined to pass close to the Sun once before escaping the solar system forever. Initially labeled C. 2017 U1, astronomers assume it's a highly unusual comet. But within a day, follow-up observations reveal no tail, no dust, no gas, no signs of traditional cometary activity. The C4 comet is removed, and it's reclassified as a 2017 U1, implying it's an asteroid. Yet even that doesn't fit. The International Astronomical Union introduces a new classification altogether, I for interstellar. The object is officially named 1I Oumuamua, which means scout in Hawaiian. Astronomers soon realize they have a narrow window to study this unprecedented visitor. Oumuamua is fading quickly, already dimming beyond magnitude 24, and they have just 40 days to gather data before it slips away. It had arrived from the general direction of the star Vega in the Lyra constellation, coincidentally, the same region toward which our own solar system is drifting. During its flyby, Oumuamua passed within 38 million kilometers of the Sunwell inside Mercury's orbit, then swung outward, heading toward the Pegasus constellation, never to return. Backtracking its journey through space is nearly impossible. Over millions of years, subtle gravitational nudges from passing stars and galactic tides have obscured its origin. It's possible that during the early chaos of a distant planetary system, giant migrating planets flung this object into the vastness of interstellar space. For eons, it drifted aimlessly until, by sheer coincidence, it encountered our solar system in 2017, but even more mysteries followed. Observations from telescopes around the world showed that every 7.3 hours, the object's brightness surged nearly tenfold before fading just as dramatically. This pattern suggested that Oumuamua wasn't a round object. It was either extremely elongated, like a cigar, or very flat, like a saucer seen edge-on, tumbling end over end. No telescope was able to resolve it clearly, so both shapes remained plausible. Then came the biggest surprise. The European Space Agency traced Oumuamua's path and detected an unexpected acceleration, about 5/millionths of a meter per second squared. This subtle push was consistent across all datasets. Typically, such acceleration would point to jets of gas, as seen in comets. But telescopes picked up no dust, no gas, no emissions of any kind. Radiation pressure from sunlight at that distance was far too weakened, lest the object had an extremely high surface area to mass ratio. Similar to a thin, lightweight sheet. But what natural process could create something that size and that thin? To investigate further, NASA turned its Spitzer space telescope toward Oumuamua, locking on with its infrared instruments for 30 hours. Spitzer is capable of detecting the heat from ordinary comets many kilometers wide, even at twice Earth's distance from the Sun, but it found nothing. No thermal emissions. Just silence. In fact, Spitzer's data deepened the puzzle. It revealed that Oumuamua's surface reflected light at a level far higher than typical comet sup. 10 times more reflective than the carbon-rich surfaces we usually see. Could the object be metallic? In late 2018, Harvard astrophysicist Avi Loeb and his team proposed a radical idea. They argued that no known natural phenomenon could explain these properties, and suggested instead that Oumuamua might be artificial, possibly a derelict light sail from an alien civilization. Their paper in the astrophysical journal Letters made headlines worldwide. While some hailed the theory as bold and thought-provoking, others dismissed it as speculative and sensational. Meanwhile, two other scientists, Daryl Seligman and Jennifer Bergner, proposed a more grounded explanation. They theorized that in the freezing void of space, cosmic rays could break hydrogen molecules free from water ice, trapping them in microscopic pockets. Over millions of years, an icy object could become a reservoir of stored hydrogen. Then, as it approached the Sun and warmed above 40 Kelvin, that trapped hydrogen could escape as invisible gas jets, providing thrust without leaving dust, gas, or even a thermal signature. They called these mysterious bodies dark comets. This theory neatly explained the unexplained push and the absence of visible emissions. Since then, astronomers have identified several more such objects within our solar system's small bodies, with measurable outgassing effects but no visible trail, reinforcing the idea of dark comets as a genuine class of celestial objects. Still, Avi Loeb remains unconvinced. He has published follow-up papers arguing that the hydrogen ice model fails to account for how quickly the object would cool during outgassing, and that it should still produce detectable effects. He continues to advocate for the light sail hypothesis, proposing that radiation pressure is the most consistent explanation. So how can we resolve this debate? One idea is Project Lyra, a proposed mission by the Interstellar Probe Working Group. The plan is to launch a fast probe, possibly on a Falcon Heavy or Starship. By 2028, it would use a Jupiter flyby for a gravitational slingshot, and dive close to the Sun for an O-Earth maneuver, gaining enough speed to chase down Oumuamua. In theory, this probe could catch up, though not until the 2050s, by which time the object will be over 200 astronomical units away and nearly undetectable. Fainter than magnitude 35, such a mission would require extreme heat shielding and propulsion, capabilities beyond anything we've yet developed. It's a long shot, but there's another, more promising strategy. Rather than chase a disappearing target, we could prepare to intercept the next interstellar visitor. And now, it seems, we've been given that opportunity. As of July 1st, 2025, the Minor Planet Center has officially listed a new interstellar object, 3IATLAS, where Oumuamua defied classification. No tail, no gas, no infrared signature. Atlas behaves more predictably, like a typical comet, and that contrast makes it invaluable. By studying both objects side by side, scientists hope to draw a clearer line between the ordinary and the extraordinary, and right on cue, the Vera C. Rubin Observatory has joined the effort. In July 2025, it captured its first full-light image and began full-scale operations. Over the next decade, Rubin will scan the southern sky every few nights, catching transient events like supernova, asteroids, and yes, more, interstellar visitors. It's our best chance yet to detect one early. While it's still inbound, so what was Oumuamua? If it was a piece of frozen, hydrogen-laced rock, it could have wandered the galaxy for hundreds of millions of years after being ejected from the outskirts of an ancient solar system. But if Avi Loeb is right, the object was artificial. Implications are staggering. It would mean that someone out there mastered interstellar travel long before humans learned to fly. It would mean Earth has already been noticed. And maybe, just maybe, a more advanced probe is on its way. Or perhaps, having passed us by, the civilization simply moved on, unimpressed. We may never know. For now, the most likely explanation remains natural. But until we can land a spacecraft, sample the surface, or catch enough similar objects to draw patterns, the mystery remains open. That's it for now. Thanks for watching. What do you think Oumuamua really was? Let me know. In the comments, if you're enjoying this journey through the cosmos, don't forget to subscribe for more.